Hello everyone, my name is Enda Murphy and my presentation to you today is about an experimental study conducted to gain insight to the physical processes driving the fate and transport of woody debris in coastal waters. Some context, logs and driftwood are ubiquitous in the world's oceans, playing a vital role in coastal ecosystems, including to provide habitat, structure, nutrients, and carbon storage, of course. It can provide a valuable source of data to support studies in a variety of fields and has many historical and contemporary uses, including an increasing interest in using large woody debris in nature-based solutions for shoreline management. On the flip side, the negative impacts of coastal driftwood are well documented. Large accumulations of debris can be mobilized by storms and tsunami, contributing to or exacerbating damage. And there are also potentially some negative environmental consequences of woody debris, or at least large quantities of woody debris in the coastal environment. So we know that the abundance and distribution of coastal driftwood is changing over time in response to human activities, climate change, and other factors. And so there's a need to understand how we can balance management practices and the ecosystem services provided by woody debris. So this requires a good understanding of sources, pathways, and fate of woody debris in the coastal environment. So to gain some insight into these pathways and driving physical processes, we conducted a series of experiments in a 50 by 29 meter wave basin at the National Research Council in Ottawa. This made use of an existing 1:30 scale coastal model, mobile bed model, and waves were generated in the basin using two banks of portable wave machines, so generating irregular, long-crested waves. And to track the movement of model debris within the basin, a high-definition digital camera was mounted overhead, taking high-definition photographs at between 1 and 3 second intervals. The model woody debris was scaled to match as closely as possible the size distributions of large woody debris observed on Washington shorelines, with data provided by Ian Miller at the University of Washington. And basically two types of debris were used in the model. Smooth dowels, which you see in the top right hand side of your screen, and then more irregularly shaped tree branches on the bottom right hand side of the screen. Essentially there were four size classes according to the length and representing prototype debris lengths between 3 and 12 meters. As you can see, each of the different length classes were spray painted a different color to enable independent tracking and analysis of the behavior of different types of debris. This is the view from the downward-looking HD camera, showing the array of probes used to record waves and currents in the basin. The experiments involve point releases of model woody debris at an updrift location in the model, so on the right-hand side of the screen as you see it here, and then tracking the movement of the debris through the model. The releases were repeated for each of the 8 different wave and water level conditions to provide statistically meaningful information. So to record the pathways and interactions of the model woody debris in the basin, we used an optical tracking technique developed by Jacob Stola, formerly of University of Ottawa and now at INRS in Quebec. And so I don't have time to go through all the steps in the optical tracking process here. But essentially this allowed us to analyze the tracks of the debris, determine orientation, look at things like variance in space to determine dispersion characteristics, residence times, and so on. So this is just a brief video to give an indication of what testing looks like when it's underway. Now I'll discuss some of the interesting observations from the experiments. So here we see two near identical experiments. So on the left-hand side, we see a release of smooth wooden dowels, On the right-hand side, we see a release of irregular branches under identical wave and water level conditions. So the first interesting thing to note is that the shorter pieces of debris, so the yellow and maroon colored debris pieces, are transported much more rapidly from right to left through the system. The other interesting thing to note is that at the end of, or close to the end of the tests, we can see that a significantly higher quantity of debris is retained on the beaches for the experiment shown on the right-hand side compared to with the smooth wooden dowels. So this suggests that the more irregularly shaped debris is much more likely to become trapped on beaches. Interestingly, the smaller pieces of debris, so the yellow and maroon colored pieces of debris, are more likely to become trapped on the rubble mound structures. Here we see an interesting consequence of a change in the shoreline configuration on the debris behavior. So here we've altered the shoreline configuration to be more parallel to the incident wave crests in the center of the shot, and we've added a terminal groin to retain the sediment. And as you can see, particularly some of the longer pieces of debris get trapped in a recirculating eddy that forms just updrift of the terminal groin structure. So particularly the longer pieces of debris tend to get trapped in a sort of a shore perpendicular orientation where the forces generated by the recirculating eddy are counterbalanced by the incoming wave forces maintaining the debris pieces in place. And it appears that there is a dependence on the length of the debris relative to the incident wavelengths in starting this behavior. So here we see some examples of woody debris that has become partly buried or buried by silica sand. So this process occurred quite rapidly, and although we know there are scale effects, the implication is that the time between wave run-up events impacting on debris is an important factor affecting the potential for beaching and remobilization. So essentially, the more time the debris spends high on the beach without being touched by waves that are sufficiently intense to remobilize the debris, the more likely the debris is to become buried and therefore less likelihood of being remobilized. So wave groupiness and inter-event durations are important there in terms of processes related to beaching and remobilization of debris. These were opportunistic experiments using an existing model, so there were some challenges we faced that perhaps could have been addressed with more time for planning. We know there were model scale effects, including viscous effects. Reynolds numbers and Coogan-Carpenter numbers were not quite in the right regimes to accurately describe hydrodynamic forces. And surface tension and viscous effects probably combined to underestimate wave run-up heights. And there were a number of other potential scale effects present. The mobile bed morphology obviously changed over time, and so this made it challenging to ensure consistency between debris release experiments. So we did try to mitigate this by periodically reprofiling the beaches and then laser scanning the topography and bathymetry between experiments. Which we can later use in our developing numerical model, which you see on the top right-hand side, to ensure at least we know what the bathymetry was for each of those experiments. Some practical issues, the debris paint tend to get rubbed off due to abrasion, either debris-debris interactions or interactions with the silica sand or structures. And although we tried a number of different techniques to retain the integrity of the paint, we just weren't able to achieve it. And so this obviously had posed challenges for the optical tracking. To summarize, we see a need for a better understanding of coastal driftwood fate and transport processes in order to inform management practices and also uses, for example, in nature-based systems. Here we used a physical modeling approach to investigate physical processes driving woody debris transport in coastal waters. and we found optical tracking techniques to be useful to support the analysis of those fate and transport pathways. We identified several factors potentially important in affecting debris mobility, including beaching and remobilization. One of those was debris length. This is particularly interesting because the length of debris is known to be a controlling factor in riverine environments, but we didn't necessarily expect that relationship to hold in coastal environments where there are fewer geometric constraints like channel width and so on. Debris morphology was found to be an important controlling factor determining the potential for beaching and remobilization. This is particularly interesting because there's substantial variability in debris morphology in the field and by region. So for example, on the east and west coasts of North America, woody debris tends to have intact root systems, potentially even bark, whereas in the Arctic region, where debris has traveled a long distance from the tree line to reach the sea, the debris tends to be much smoother and more aligned with the sort of wooden dowels we saw in the model experiments. The time that a piece of debris spends on the high beach is an important controlling factor determining the potential for remobilization. The longer the piece of debris spends on the beach, the more likely it is to become buried by sediment. And so the clustering of wave run-up heights is very important in determining how likely a piece of debris is to become deposited and remain so. I've also listed several other potentially important factors that I don't have time to discuss in great detail here today. Directions, we've identified a need for more controlled physical model tests of much larger scales to eliminate some of the scale effects we identified. But the experimental data here will provide a useful basis to inform the development of a Lagrangian particle tracking model, which we hope to use to describe fate transport processes for coastal debris. So here are some references. Thanks to all my collaborators, particularly my co-authors Andrew Cornett and Ewan Nister, and also a special mention to Alistair Rayner from the National Research Council of Canada for his support in executing the experiments described here.